All right, that was question 15 from chapter 16, part C. I guess I have to complete this. Let me fix this. This is extraction of iodine from water. Iodine is I2. I2 is nonpolar. So water is quite polar. So iodine being nonpolar isn't the most soluble in water. We'd say it's insoluble, but that doesn't mean it's 100% insoluble. Some iodine will dissolve in water. But it turns out iodine is considerably more soluble in carbon tetrachloride, which is nonpolar, than water, which is quite polar. At a certain temperature, the concentration of iodine in its saturated aqueous solution is 1.3 times 10 to the minus 3 molar. Our cutoff is 10 to the minus 1 molar. And so since this is below our cutoff, we call it insoluble. But still, it's, you can put in 1.3 millimoles in a liter. And the equilibrium achieved when iodine distributes itself between water and chloroform is this. This is called solvent extraction. That is, if we use some chloroform and water don't mix. Chloroform actually is more dense than water, so chloroform is not like oil. Oil floats on the surface of water. Chloroform sinks to the bottom of water, and it forms a layer of liquid chloroform on the bottom.
I know there was this one Chem 1A lab where we had to use chloroform for something. Was it just a straight up chemical? Like, was it not dissolved in anything?
No. You did this in Chem 1A. This is called solvent extraction. So let's say iodine was a product or iodine was a reactant. What you try to do is add some chloroform. And the thing is, iodine, sometimes the color is faint. And so what you can do is you can concentrate the iodine into a small layer. You want a small layer of chloroform. If you use a large layer of chloroform, you're defeating the purpose. Because what you want to do is you want to highly concentrate the iodine so it becomes bright purple. And so you should have gotten bright purple color from this. And so we do this. What we do is we cork it and shake it up, and we create an emulsion where the chloroform droplets disperse in the water layer. But the emulsion is not stable. There's emulsifiers, like in mayonnaise, they can do it. But it's going to separate. Like mayonnaise, you can mix the oil and the water, and it stays emulsified. Here, the chloroform layer is going to sink back to the bottom, but when it sinks back to the bottom, it is successful extracting a lot of the iodine out of the water layer because iodine prefers the nonpolar chloroform. In other words, water prefers to be around polar water, and so water kind of kicks the iodine out. All right, it's not 100% effective though. Here, K is 85.5. It's not a huge number. And so what we can do is we can get more of the iodine to dissolve in chloroform than in the water. And they tell us this. This is called the solubility. We have two types of solubility. One is the actual solubility, how much quantitatively dissolves. And the other solubility is the qualitative solubility. That is, this would be classified as insoluble in water. So part C is asking for what? If the 20.0 milliliter sample of saturated iodine, aqueous, in part A had originally been extracted with 40 milliliters of chloroform, how many milligrams of iodine will remain in the aqueous layer when equilibrium is reestablished? So we're just going to extract more iodine. If we use 40 milliliters versus what was used before, you can calculate it. 20 milliliters, so you double the amount. If you double the amount of chloroform, then you should double the amount of iodine that gets dissolved in it. And so if you double the amount of iodine, we got to figure out how much iodine goes into the chloroform layer. And so what you do is you take a look at how much iodine went into the chloroform layer. This is the milligrams of iodine left in the aqueous layer. So how many milligrams did you start with? How many milligrams did you end with 20 milliliter extraction? And then with a 40 milliliter extraction, double that. And so you figure out how many milligrams of iodine you start with, double the extraction, and then figure out how many milligrams you're left with. It should be this. I mean, was that kind of the question, or what?
Why is it directly double? Like, I understand that increasing the amount of...
Well, like if you have, let's say, if you have 1 gallon of water, 1 gallon of water weighs 8 pounds, right? And then 2 gallons of water should weigh 16 pounds. And then it's like, okay, if you make saturated iodine in the water, okay, you're going to have, in 1 gallon, half as much iodine as you would have in 2 gallons because it has to have the same amount per volume ratio. In other words, the same concentration. So you're going to have twice as much iodine in 2 gallons of water than in 1 gallon of water, just like you'd have twice as much iodine in 40 milliliters of chloroform versus 20 milliliters of chloroform. And so that's one way of doing it. I mean, there are other ways you could do it, you know, based on the, you know, the concentration of the iodine in chloroform. You just take 40 milliliters, convert it to liters, you know, the molar concentration. Do it that way. Does that? This is more a practical application. It doesn't quite click though, or?
Not quite yet.
Not quite. I mean, we could just do it very qualitative. How about that? Let's just look at this qualitatively. Sorry, this is not chloroform. You guys in the Chem 1A lab use chloroform. Chloroform is CHCl3. It's still very nonpolar. This is not chloroform. This is carbon tetrachloride, which is even less polar than chloroform. So if you have 20, let's say I have, let's say this is saturated, and I don't know how many. Let's say I have X grams of iodine in here, and it's saturated. So what I'm going to do is I'm going to double it. So I'm going to go 2 times 20 milliliters of chloroform, or no, sorry, carbon tetrachloride. That gives me 40 milliliters of carbon tetrachloride. And so I'm going to have twice as much. And how much iodine? Well, I'm going to have double the amount of iodine. So it's going to be 2 times X grams of iodine, because now I have twice as much. And so I should have twice as much carbon tetrachloride, and I should have twice as much iodine. Does that make sense at all, or no? Yeah. Yeah, it's just getting twice as much of the same solution, essentially, is one way of thinking about it. I don't know if somebody else has a better explanation. Help me out with that. But you can ask me also after the break. All right, Gavin, what was your question?
Yeah, I have a question on like question 3 of the quiz. I was just curious because I think I was using the
Question 3 from the quiz.
Yeah.
Yeah.
All right.
You said that K doesn't have like units, but then the question said KC, and KC has like 1/2 Celsius. It has units of like molarity.
Yes and no. Kc is the numerical value of the ratio. It's the product to reactants ratio using concentrations. So what we do is we just plug in the concentrations here. They're going to be molar concentrations using molar concentrations. So we plug in the molar concentrations, G, G, etc., A, etc. And the molar concentrations do have units, molarity. But what we do is we have to convert these into activities. So we could, the molarity is what we call the stoichiometric concentration. We have to convert these into activities, which are called what? Concentrations. Activities are known as effective concentrations. So how do you convert it? Well, the way we convert from molarity to activity is activity is equal to this factor here. I'm not going to get into it. Times the concentration. This factor is going to contain the units molarity, and the molarity contains units of molarity. So what ends up happening when you calculate the activity of this is the molarity cancels the molarity, and the activities come out to be dimensionless. Now the K's are meant to use activities, because if we use concentrations, the concentrations will fail us as the solutions become increasingly concentrated or increasingly dilute. As the solutions become increasingly concentrated, this will fail us. And therefore, we must, but in reality, we're supposed to use activities for everything. And the activities themselves are dimensionless, therefore K, we say, is dimensionless. Because had we done it correctly and used activities instead of concentrations, there should be no units. So Kc, Kp, and Keq should be dimensionless, because that's how the activities work.
Are the activities just the same value, or is there like something that you're actually?
Oh, there's something you're actually multiplying here. Actually, let me not do it. This one. You can use ChatGPT to show us. We have something called the activity coefficient, which is denoted by the Greek letter gamma. It's a dimensionless factor that corrects for the non-ideal behavior of solutions. And so all we do is we correct it using activity coefficient. It's not difficult, but you need the data to do this. So one, we could determine, actually we just look it up in a table. But how do you determine these activity coefficients? How do you determine, one way of determining it is by theoretical studies. That is, you can look at, how strongly the ions attract to each other and how much ion pairing occurs, theoretically. Or two, you could just measure it. What are different ways of measuring? One way of measuring it is by colligative properties. This is why this was in the colligative properties section of chapter 14, is because the colligative properties, that is boiling point elevation, freezing point depression, and osmotic pressure, depend on not the stoichiometric concentration, it depends on the effective concentration of all solute particles in solution. And so one way of measuring how much it deviates is by just measuring the boiling point elevation. something that can be done. And so you can determine it experimentally, you can determine it theoretically. Remember, we have a two-pronged approach on everything. You know, we'd like to solve everything theoretically, but sometimes the theoretical part is complicated mathematically. And so we have the empirical approach here. And so two-pronged approach to solving for activity coefficients and solving for deviations from ideal behavior, either experimentally or theoretically. And this is why I ask you questions like, where did that K expression come from? Did that come from a theoretical analysis, or did that come from an experimental analysis? Because, you know, people want to know that kind of stuff. So the actual equation is not terribly difficult. Let's see here. But anyway, in an ideal solution, the activity coefficient would be 1. So in an ideal solution, the effective concentration is the same as stoichiometric concentration. Real solutions don't always follow this. Just has like real gases, so we have to modify. We use the van der Waals equation when we're dealing with a real gas, something that's going to deviate from ideal behavior, and then we'll do the exact same thing for this. It's not, you know, all that different. It's just an extra step that you have to do. So I said that activities are dimensionless, and therefore K should be dimensionless. Even though, you know, we need to know the dimensions, because KP, you know, depends, the ratio is going to depend on what units you use. If you're using torr or millimeters of mercury, you're going to get a different numerical value than if you're using atmospheres. If you're using atmospheres, you'll get a different numerical value than if you're using bar. It depends on if the units cancel in the K expression. If they don't cancel, then it makes a difference what units you use. If the units do cancel, then the conversion from millimeters of mercury to atmospheres is the same for the numerator and denominator, and that therefore doesn't make any difference. And so there are different scenarios where those things occur. And it's just seeing a lot of different scenarios. Familiarize yourself with it. So does that make sense, that question?
Partially.
Yeah?
More sense now, yeah.
Okay.
I'm still kind of iffy on that. Can I write something on the board and kind of see if you can explain it to me? So in this case, it feels like if we have m times m and then m on the bottom, it doesn't, the units don't cancel out.
Units don't cancel, right.
So in that case, we'd have like Kc is equal to some value times m?
No.
No?
No.
So they don't
No.
have to cancel?
We're talking the numerical value.
Oh.
I'm saying. So let's say I want to convert this to a different unit. So as an example, let's say I want to convert this to some other unit. Let me do it like this. What I mean by cancel is something different. Here, I'll just write it up here. Easier. You could look it up. It's all right. Go on. Here, let's say we measure these in atmospheres here. And so what we get is we get B pressure over A pressure. What I mean by the units don't cancel, here in this case the units do cancel, atmospheres and atmospheres, right? And so if I measured these in millimeters of mercury, would I get the same ratio or would I get a different ratio? And so this is millimeters of Hg, this is millimeters of Hg. Would I get the same ratio or different ratio? It turns out I get the same ratio, because in order to convert atmospheres to millimeters of mercury, I just do this: 760 millimeters of mercury on the top per atmosphere, and then on the bottom I do the same thing: 760 millimeters of mercury on the bottom per atmosphere. And you see that the conversion factor cancels itself out. So when the units can cancel here, then it doesn't matter if I use atmospheres, millimeters of mercury, or bar, I'm going to get the same ratio, the same numerical value. That's what I mean by cancel out. However, if they don't, let's say A goes to B plus C, then I'm going to get a different number, numerical value, because the conversion factors don't cancel out and it doesn't work out. So it's going to be important that you keep track of the units, because to be on the safe side. But all the K's are dimensionless, because we should be converting all of it. It's just special cases when the units work out, like delta N of gas is 0, When the units work out, then you have additional mathematical relationships that hold. Now, these mathematical relationships are what cause a lot of headache for chemists and students. So there's a bunch of mathematical relationships. So for example, is delta H the same as delta H naught? Are they numerically the same for the same reaction? The answer is or what is the difference between these two? And so all these things, sometimes, they could be the same or they could be different, And so we need to know certain things. So, for example, I didn't specify the temperature. This could have been temperature T1. This could have been at temperature T2. Because under standard conditions, we don't know what the temperature is. And so, if they're at the same temperature and then this has, certain pressure or whatever. And so there are things that sometimes it works out and sometimes it doesn't. But these are all mathematical relationships that you encounter. And the more of those you know, the better. Because then you can do little tricks to speed up things rather than have to do it the long way. And so the same thing here, we could figure it out. We can go through all this, I'll convert it and do all this stuff, and then I come up with the same answer. Well, I could have just saved myself 5 minutes, had I known. But the shortcuts you do after you learn the long way. You got to learn the long way first, and the long way is these are dimensionless, but we got to worry about the dimensions, this kind of stuff. All right, other questions?
I think we went over this last night, but is it that KEQ is always equal to KP if like all reactants and products are gases?
Mm-hmm.
And then KC is equal to KP if they have the same amount of moles of gases on either side, and there's no aqueous. Okay. And then KC is always equal to KE. No.
That last one's not good. So for example, if we had A gas goes to B, or G gas, I should say G gas here, then KEQ is equal to KP, which is not equal to KC. Or actually in this case, because we don't know what A and G are. If A and G are the same, then KP is equal to KC. And so we say is equal to KC if A and G equal. Or, all these little mathematical relationships we have to keep track of. But the other thing you could do is you could just work through it and see, the long way.
So KEQ and KC are the same if they have the same amount of moles?
No, KEQ and KC are the same if they are aqueous. If AA aqueous and GG aqueous, then KEQ is equal to KC. Now there is no KP for this because there's no gases. And so in this case, KEQ is equal to KC. And all of this you can figure out because the activity of a gas approaches its pressure, and the activity of a solution approaches its concentration. Now, there are cases where it doesn't matter what you use. Remember when we were at the very beginning of this chapter, we had a scenario where we used moles instead of molarity. And you could do that if the number of moles of solution on the left is equal to the number of moles of solution on the right. And then we could use moles. And so what that means is that numerically, for that particular problem that we did, if it consisted of gases, then we get the same K value for KEQ, KC, and KP. All of them would be the same. But you don't have to worry about that. What you could do is you could just calculate it and see. That is, when we're dealing with gases, it's always the pressure. When we're dealing with solutions, it's always the concentration. KC's concentrations, KP's the pressures. And then you see if KP and KC are equal. They're equal when delta N of gas is 0. And that way you can figure it out. Quiz 3. I didn't put this up here. So here, graphite plus CO2, is this KC? Is KC and KP, are they equivalent? Yes. They're equivalent. So in this one, KEQ is equal to what? This first reaction here. KEQ is equal to KC or KP? KEQ, this is gases. So KEQ is not equal to KC. KEQ is equal to KP. But delta N of gas is 0. Therefore, KP and KC are the same. Which means KEQ and KC will be numerically the same. But theoretically, they're not equal. KEQ is equal to KP. Numerically. But conceptually, they're different. KEQ for gases is pressures. You see, I don't have any units there, but the origin of the ratio comes from the original pressures.
But I thought you said that if it's all gases, then KEQ equals KP.
Yes.
But they're not all gases because it's graphite.
Oh, yeah. What I mean by all gases is graphite has an activity of what? 1. So we don't care about graphite. We care about everything else. The same thing, if there's a pure liquid in there, we don't care about that either. We're looking at whatever else we have. And so in this case, it would be the same. The graphite will have an activity 1, and it's incorporated into both of those. And so what I'm saying is that they're numerically equal here. This one's all gases, so is KC equal to KEQ? In this case, KC is equal to KP, and KP is equal to KEQ. But all three are numerically the same. Just conceptually, they come from different places, so we just track it. We track where they come from. This is a little bit like waves and probability functions. We can't tell where it came from. like if you go back to wave functions, psi. What's wrong with this here? I got a new tablet, but maybe Word may be about to crash. I'm going to delete this. Start closing some of these.
Because you have so many tabs open, it's like slowing down the computer.
Yes. I'm going to close some of these.
I'm not sure if this is a feature on Chrome, but on Firefox, there's a feature where you can save your tabs,
Okay.
where you can close it, which I assume would speed up your computer and maybe cause Word and Excel to crash less. But when you open up Chrome again, it would keep going tabs.
Yeah. I'll maybe try that next time. Although it doesn't use much memory. And so it used to be in Windows you could allocate how much memory. So I've allocated the maximum amount of memory to Word when I've been getting all these crashes, but it limits it. It used to be I could assign, this is back in the days when we had very little RAM, and then you could assign some hard drive space to RAM.
Well, the thing is that code takes up a lot of RAM.
Yeah, although I have a lot of RAM on my computer. Yeah. And so I'm only using 47%, of which 29.5% is taken up by Chrome. And so I have more than 50% of my memory free. Word is only using 2% of that. But I'll try it anyway.
Throwing it out there.
Yeah. Yeah, no, I appreciate it. Suggestion. For sure. I've tried a lot of different things to prevent this. It didn't happen with my Dell. That's the weird thing. We had Dell computers before, and then everybody got switched to HP. So I'm using the HP ProBook, and that's when it started. But I have the same amount of RAM. I upgraded this RAM. I think I have 24 gigs of RAM on this. Can't remember. Because I thought it was a RAM issue. So I went.
4 gigs on a laptop? Wow.
Yeah, I think, it was 16 I think I had, and just I got another 8 gigs of. I have 16. I have two slots. So one's a 16, the other's an 8. I think. But anyway, yeah, 24 gigs. I thought it should be plenty. Anyway, what I was saying is about the wave function. So certain things we keep track of. Let's try Excel. So if we have a wave function, let's say 2p, then it looks kind of like this. Where we have positive amplitude and negative amplitude and a node here where it goes through 0 amplitude here. Do you remember something that looks kind of like this? And then we do our orbital. Our orbitals are psi squared. 2p. This gives us a probability distribution. And our probability distribution is going to look like this. Like this. And so we end up with a 2p orbital that looks like this. Or actually, let me draw it like this. We end up with a 2p orbital that looks like this. Oh, it's dead. We're going to have an electron cloud here and electron cloud here. And so we have 2 lobes, and then there's a node in the center, and then we draw our probability boundary. Our probability boundary would be something like this. Now you can't tell which of these lobes came from positive amplitude and the negative amplitude. We lose that information. And so that's called phase information. So to keep track of the phase information, we put these signs here that this lobe came from the positive amplitude and this lobe came from the negative amplitude. And so oftentimes when you see orbitals, they'll be marked with a plus and a minus, stating that when we square it, we're going to lose that sign information. And then when you square root it, then you don't know. It's either plus or minus, right? Square root of 4 is plus or minus 2. So we lose that. When we go dimensionless, we lose that information. Therefore, when I say Kp, I put in that information in there. I said Kp in atmospheres. Or I said Kp in this, in bar. I lose that information because we go dimensionless, so then I reinsert it. Just like in orbitals, we do this. We color the lobes different colors. So oftentimes people color red and blue. You know, so one lobe is red, the other is blue, or whatever color scheme they want to use. Or they use signs, plus sign, minus sign, you know. That way we don't lose that information. And so they're dimensionless, but I say it's yes and no. Of course, they depend on molarity because that's where you get it. Well, the same thing here. These are both positive amplitude, the psi squared, but yes and no, they depend on the sign of the wave function. And they're going to react differently depending on that sign. It's something like that, you know. And so that's why I include the units in there. Well, Kc is always with molarity, but Kp need not be. And sometimes they're equal. And sometimes it doesn't matter what pressure unit you use. You know? Sometimes it does. Kc is always in molarity. For us, it's always going to be in molarity. We aren't going to use any other units for Kc other than molarity.
But it doesn't actually have units.
Hmm?
It doesn't actually have units.
Yeah, right. It doesn't actually have units, right. But, you know, if you were to use different units, you could get a different number for Kc. All the Kcs on our book are based on molarity, molar concentrations. Right. And so they depend on it, but the actual K is dimensionless. The actual amplitude of my psi squared wave, the probability is positive, right? But it depends if it came from a negative squaring that or came from a positive squaring that. Why does it matter? It matters because chemistry happens in 3 dimensions. And when you're doing a linear combination of atomic orbitals, if you do a plus to a plus, we get a bonding molecular orbital. If you do a plus to a minus, we get a anti-bonding orbital. There's 2 ways of overlapping these two. If I had 2 p orbitals, you can overlap the negative with the negative. Well, that's going to make a bonding. Or you flip this orbital around and you overlap a negative and positive. Negative and positive creates an anti-bonding orbital because of destructive interference of waves. And so even though when we look at the orbitals, yeah, they'll overlap, we need to know the sign of that orbital to see, does it really overlap or will it destructively interfere? You know? But you can't see the sign by looking at the lobes because the lobes look exactly the same. You have a lobe here and a lobe here. It looks like a figure 8. They look exactly the same. You can't tell the difference. And so we have to take a step back and look at the phase information. Just like K. You can't tell K, so we take a step back and look at where it came from. Did it come from molarities? Did it come from atmospheres? Did it come from bar? That's why we need to know that, but it's not inside the K itself. Just like the sign is not inside our electron cloud distributions. You know, we just have an electron cloud distribution, that's it. Well, don't worry, I mean, don't worry about the units because we never include the units in the actual K, you know, calculation. So you would have molarity the minus or molarity the positive one. We never include that in there, so don't worry about that. All right, are there any other questions on this? Okay. There are certain techniques that you need. You need to be able to calculate K value, you know, from given. And you have to be able to use the K values. And using the K values, there are certain techniques that you need to be able to do. Like, for example, are you comfortable with resetting the initial conditions? Sometimes we'll have to reset. In this particular one, we wouldn't necessarily reset. I mean, 23.8. But on other problems, it would be crucial to reset to make the math easier. But there are other tricks in addition to resetting. One of the advantages of resetting is that the change is small. If the change is small, then you can try the simplifying assumption. And so I could just give you a brief rundown here, since I give the morning class this too. So this was a problem that was asked in the morning. Was this H2S yields 2H2 and S2. So this is a redox decomposition. So this is going back to the elements in elemental form. This is an unusual form of sulfur. This is diatomic sulfur, which is a gas. It's like diatomic oxygen. But anyway, Kc is equal to 4.20 times 10 to the minus 6. In this case, is Kc and Kp, are they equal? Kc and Kp, are they equal? No, they're not equal. Delta N of gas is, what is delta N of gas for this? Plus 1. And so Kc and Kp are not equal. However, Kp and Keq are equal because Keq for gases is Kp. The Kc of 10 to the minus 6, would you reset this? This one heavily favors what? The reactant or the product? Reactant. So I wouldn't reset this. You know, I'm given 0.5 initial here, 0, 0. So that seems fine. You know, what we want to do is we want to approach equilibrium from the direction of least change. This would be the direction of least change because this heavily favors reactant, so it should stay reactants mainly. But the change is going to be minus 2x plus 2x plus x here. And so at equilibrium, we're going to have 0.500 minus 2x, 2x, and x. Ignore all this other writing since I'm just going to go through this quickly here. And so this is the K expression. And so if you do get the wrong answer, make sure you have the ICE table and the K expression. You'll get partial credit for that. All right, so we'll plug in the H2. The H2 is 2x quantity squared. That gives us 4x squared. S2 is just x. And then the H2S is 0.500 minus 2x, which gives us 4x cubed divided by 0.500 minus 2x. This is a cubic or third order polynomial. If it's cubic, then we could get it into cubic form, and you might have a calculator that solves quadratics and cubics. If you do, then you can get a cubic form, ax cubed plus bx squared plus cx plus d is equal to 0. And then punch A, B, C, and D into your calculator, you'll get the answer for x. That's one way. It's using no assumption. The other thing we could do or try is the simplifying assumption. If we tried the simplifying assumption, which one should we say? Well, we're going to say that 2x, the change, is much smaller than 0.5. So the simplifying assumption says 2x, the change, is much smaller than 0.5. We don't know if it's true or not. Here. So using the simplifying assumption here, that means 0.5 minus 2x is just 0.5. And so this is going to be 4x cubed divided by 0.5 squared. That's going to equal that. And so this turns out to be a simple math. We don't need a special calculator for this. Just cube root. And we get 0.064. And then we calculate the percent change. The percent change is the change. The change in this case is 2x. Sometimes the change is x, sometimes the change is 3x. We have to look at the binomial and see what the change is. In this case, it's 2x over the initial 0.5. That gives us a 2.56% change. 2.56% change is a little on the high side. You know, I'd start to worry about error in this. You know, because what's the maximum percent change? 5%. And when you're at 5%, you got to expect some error. in your x value. And here, this is kind of big, so I'm expecting some error in my x value here. So if you don't have this calculator that can solve the cubic, because if we could solve the cubic, then there's no assumption there. If you don't have that calculator, then what we can try is we can try successive approximations. Because successive approximations, here, we don't have to make any assumptions. See, we're going to retain the change, so it's 0.5 minus 2x. We're not going to get rid of that change. And so what we're going to do here is we're going to use successive approximations to do it. And then we're just going to take a guess. The best guess is this, 0.0064, what we got from the simplifying assumption. So what I'm going to do is, I know this is off a little bit. It's still acceptable, but maybe I want a more accurate answer. If I want a more accurate answer, then I'll try that. And in this case, we'll just start with this. I know this is going to be off a little bit because it's a little high as far as the percent change goes. So I'm a bit lazy. And so what I do myself is I just do this in Excel. And so in the first column here, I put in my guess for x. If you're doing this by hand, the answer we got from simplifying assumption is 0.0064. Let's say the simplifying assumption failed. If the simplifying assumption fails, then you definitely have to go to successive approximations. And if you go to successive approximations, make your life easier by just going 1 sig fig initially. So that's what I did here. I want 1 sig fig. And then what I did was I just punched in the equation for this, the equation up here, which is 4 times a2, which is x cubed, divided by 0.5 minus 2 times x, which is a2 squared, 180 squared. And so I have the equation set up there. And then I'll just have Excel do it. And so at 0.006, I have 3.62. That's too small. I need 4.2. Then I went to 0.07, and I got 5.8, too big. Then I went to halfway between, 0.065. It's giving me 4.6, still a little bit too big. So I went to 64, which got me 4.4. I went to 63, it got me 4.2. But it got me 4.21, not 4.20. I want 4.20. Then I went to 62, it got me 4.00, went way too small. And so it's going to be a lot closer to 63 than 62. Then I went to 62.629, which gave me 4.18. Very close. This would round to 419. And so then I went halfway between 629 and 630. So I went 629.5. And 629.5 gave me 4.20009. So this is great, because to 3 sig figs, it's right on, 4.20. And so my x value should be 0.006295. Okay, that would be more accurate than the x value I got from the simplifying assumption. The x value I got from the simplifying assumption was not 0.006295, it was 640. Do you see how off it is? It's off because our percent change was kind of big. So if I do this, what I need to do is don't stop here. Some people stopped here on the quiz. You don't stop here. I don't want x. You know what I want? I want the equilibrium concentrations. And so you got to write in the equilibrium concentrations. But you have to be careful because I make mistakes too. So for example, I did 0.5 minus x. I did 0.5 minus x and I got this in yellow, 0.495705. But that's actually wrong because it was 0.5 minus 2x. But how I found out I was wrong wasn't because I saw it. How I found out I was wrong was I got this concentration, then I got 2x here, and then I got x here, and then I plugged it into my k expression in purple here. When I plugged it into my k expression, I got a k value of 4.06 times 10 to the minus 6. But the actual k value is 4.2. And so that's a big difference. And if you know, look how many extra digits I carried. I carried a lot of extra digits. So the difference in the k values is not due to round-off error. The difference is due to a calculation error. And so if I get a mismatch like this, it's supposed to be 4.2, I get 4.0, 4.06, then I'm way off. I'm way off. So then I went back and looked for my mistake, and I found my mistake here. I forgot to multiply this by 2. When I multiplied this by 2, it gave me 0.48741. And now if I cross this out and put 0.48741 squared under here, I get 4.200 times 10 to the minus 6, which is good. So what we want to do is we always want to double check to make sure we didn't make a simple algebra error or something else. Sometimes it's hard to find, but you just go back and redo the problem if there's a mismatch. But you have to carry extra digits because you don't know if it's a rounding error or a calculation error. So I wanted to just mention this particular problem here. Okay, sometimes you have to do the method of successive approximations. Okay,
When you did your method of successive approximations for this problem, did you try out like 0.1 and then 0.2 and then found out that 0.1 was a little closer and then you just tried between 0 and 0.1?
Yeah, well, what are the limits here? Let's say I didn't know what my first guess is going to be. If I didn't know what my first guess is going to be, the range, we'll figure out the range, which is in purple here. It has to be greater than 0 because we can't have a negative molarity. So x has to be greater than 0, but it cannot be greater than 0.25. Because if I have x as 0.25 here, then 2 times 0.25 is 0.5, and that gives me 0 here. Any x larger than 0.25 will make the negative term larger than the positive term, and that will give me another negative molarity. So what I do is I guess anywhere from 0 to 0.25. And so I could start at 0.1, go to 0.2, and then start narrowing it down. Okay. The danger of this is getting stuck in a small well, because we don't know the shape of the function. And so the danger might be we're stuck here and it never converges. If we're stuck here and we're adjusting it and we get closer and then all of a sudden we get farther, and then we try going back and forth, we're stuck in a well, so widen out the window. Try to find another potential well to minimize. Does that make sense? There. So if you're getting stuck, you might be stuck in a trap in the mathematical function, and so you need to widen out the window to get unstuck. It's like the fish, the fish, the pond is evaporating and the fish is stuck in a little puddle, and the puddle's shrinking smaller and smaller, And I saw this on YouTube, and I don't know how the fish recognized the fish had to jump out of the little puddle and then wiggle its way back into the lake. It was weird. I don't know how it figured out the lake was over there.
Was it like a lungfish or something?
It wasn't a lungfish, and it just realized it was in deep trouble, and so it just did that. It was pretty interesting. That I thought, how did it know which way to go out of the puddle? It could have went the wrong way and got stuck. And it seems like it. Maybe maybe it could smell the humidity. But this is the same thing. You could get trapped in a little puddle here, and so widen out the area and see if you can get. All right. Any other questions? No. What I'd like you to do is this. I'd like you to take a look at your crystals, and then. Maybe take a picture of it. If you're not getting any crystals just yet, add some more ethanol. We should have some ethanol in the hood over there. And just add enough to get either crystallization or 10 milliliters. And then put it back in your drawer. Then take a break, and then we'll start the test after that.